All right, we're ready to talk about the other two groups of rocks, sedimentary and metamorphic. And if you remember from the rock cycle, sedimentary rocks are made up of pieces of pre-existing rock, and metamorphic rocks are rocks that are changed due to heat and pressure. Actually, in this section, we're going to get a little bit more into that definition. It's a little bit more detailed than those simple definitions. All right, so sedimentary rocks are formed from pieces of pre-existing rock that has been weathered. Sedimentary rocks are the most common rock found at the Earth's surface. They make up about 75% of all rock outcrops. A lot of people go on road trips. You go to the Grand Canyon, maybe you go to Zion National Park in Utah. You're going to look at outcrops of sedimentary rocks. They're pretty darn impressive. Now, they cover nearly all of the ocean floor. I told you before that the seafloor is lined in basalt, but sitting on top of that basalt are sediments and sedimentary rocks. Sedimentary rocks are pretty easily eroded for the most part. The cliffs of Santa Barbara, where I grew up, erode at a rate of 1 to 2 feet per year. Okay, that means that places that when I was a little kid, some of my friends' houses that lived on the cliffs had big yards, and in 30 years, there's at least 30 feet less of that yard, and sometimes it encroaches on the house, and sometimes the houses get condemned. Now, if you can remember seeing distinctly layered rocks like you would see in the Grand Canyon, you are probably looking at sedimentary rocks. Sometimes lava flows do this, like at the Columbia River Gorge. But typically, if you're looking at layer cake rocks, you are looking at layered sedimentary rocks. All right, sedimentary rocks are so important because, we use them to figure out Earth's past. You guys, if you climbed Mount Everest and I asked you to bring back a rock and you brought me back a rock, we'd look at it and it's marine. It's from the bottom of the ocean, not too deep, but there's actually marine fossils in the rocks at the top of Mount Everest. So you know that it hasn't always been, 5 miles sticking up in the air. Fossils are very important because they do tell us about the past. We'll talk a little bit about fossils in the last section, but if you guys are really into fossils, you need to take the historical geology course. That's much more into fossils. Come walk around our museum. We have a lot of fossils. Again, time indicators. If you guys came in and you'd found a fossil and I said, oh yeah, that's a trilobite, I could tell you how old that rock was in general. Okay, we could get a lot more specific too. So, you find rocks that have dinosaur fossils in them, then I could tell you, oh, that's from the Mesozoic and give you an age range. Now, we can also use fossils to match the age of rocks across different continents. And so we're going to talk a lot about that in our geologic time section. All right, sedimentary rocks, a lot of them are economically important. They are our source of fossil fuels. Coal is the remains of ancient plants. Petroleum and natural gas are typically the parts of diatoms or ocean organisms. And remember when we talked about banded iron formation and I told you that's what they mine to make steel? That's a sedimentary rock, so they're pretty darn important. You drove in on it, you put gas in your car, and the electricity that, powers your house, about half of it comes from coal burning power plants. All right, if you remember on the rock cycle, we had a lot of steps to make a sedimentary rock. And obviously some of those steps are much more important. You got to take whatever pre-existing rock you have and uplift it to the Earth's surface because it's the external heat source of the Earth, or the sun, that powers the atmosphere and the hydrosphere and works on tearing apart and breaking down our rocks. Okay, so we have weathering, erosion, transport, deposit, burial, compaction, and lithification. So we'll talk about the really important ones, and weathering is a really important one. All right, weathering is the physical and chemical breakdown of rocks and minerals at the Earth's surface. At or near the Earth's surface, you have to be in contact with the atmosphere or the hydrosphere. Sometimes it's a very long, slow process. I have pictures of Yosemite from 100 years ago that, parts of them look exactly the same as today. Sometimes it goes a little faster, like those cliffs of Santa Barbara. So weathering is such an important step, okay? It makes soil, and, you like to eat, so you better believe me, you care about the soil. It's what makes the ocean salty. Products of chemical weathering go down into the ocean and accumulate there and reach an equilibrium and have made the ocean salty over time. and they provide the nutrients that are necessary for the base of our food chain for those organisms that photosynthesize and things. So pretty important. All right, there are two different types of weathering. There's physical weathering, okay, or the physical or mechanical breakdown of rocks. Imagine this. There's a big, beautiful piece of granite, and I say, oh, I'm going to break off a piece. It's really neat. And then every student behind me says, oh, I want a piece too. So I sit there with a sledgehammer, and we break off piece after piece, and we all hold it up and say, hey, we've got granite. Okay, it's all identifiable as the same stuff. It's just broken into smaller pieces, and we'll talk about how nature does that. Okay, chemical weathering is the chemical breakdown of a rock. A piece of chemically weathered granite looks very different from a piece of physically weathered granite. If I put chemical weathered granite in your hand, you wouldn't like me. Okay, it's dirty. It's clay and silt and ions in solution and gravel, and it looks very, very different. And we'll talk about different types of chemical weathering. All right, so physical or mechanical weathering, breaking a rock just into smaller pieces that is clearly identifiable as the same rock. It just makes a big rock smaller, which makes it obviously more easy to erode and transport. Now, I'm going to tell you about 5 different types of physical weathering. You guys be able to name and briefly describe 2 of these, any 2 you choose, okay? And I'm just going to tell you ones that are easy, ones that are local, etc. That, these are the 5 main types of physical weathering. All right, frost wedging happens a lot in our area and is pretty easy to understand. I think everybody has probably in the past, you put a soda in the freezer and you forgot, whoops, boom, or a beer. Okay, my brothers did that. And they explode. And they explode because when water freezes, it expands almost 10%. So, all you need is a little moisture. It can rain or have dew. Rocks have cracks in them. We're going to talk about why rocks have cracks in them. And that water gets down. Now, a lot of nights, especially in the winter, it freezes. And so that water would freeze, it would expand, and it would act just like a crowbar and pry apart the rock. If you look at B, the picture B there, look on the bottom on the right, you see a little fragment of that rock, and it's easily identifiable as being the same material as the bigger piece. So frost wedging is a great example of physical weathering. Okay, here is a granite boulder up in the Sierra that has been frost wedged, and if we were very patient, we could take glue and just glue that boulder all back together. It's very easily identifiable as all the same stuff. All right, pressure release. This is also something that we find a lot in the Sierra because they're granite. Now remember, granite's formed 5 to 7 miles beneath the Earth's surface, and it cools and solidifies. And then, how did it get exposed to the Earth's surface? The overlying material was eroded away. Now, if you had 5 to 7 miles worth of stuff sitting on you, and then it was removed, you would expand. And because it's solid, it expands brittly. So think about it, you guys. The Sierra is full of domes, like half dome. Half dome's a dome because it's granite and it formed this way, but it's half a dome because of glacial activity that happened later that we'll talk about. So as it expands, you can see it cracks horizontally and vertically, and it there's a lot of different names for pressure release: exfoliation, spalling, sheeting, etc. You can see parts of the granite are still covered, so that's why they didn't rise up as much. So you get this dome type, and then it breaks off kind of like the layers of an onion. Okay, so on the right, you've got a dome. On the bottom right, you've got a dome. It's not half dome. It's another dome in Yosemite. And on the left, this is part of Yosemite that's called Tuolumne Meadows, a little bit less populated part of the Yosemite National Park. And I call this the Stairmaster from hell. If you guys worked here and you climbed those steps, if you had long enough legs, you would have buns of steel. So you can see the horizontal breaks, you can see the vertical breaks. That is this exfoliation or sheeting or spalling or pressure release that you find occurring a lot in granite because it's expanding as that overlying weight of the rocks is removed. All right, salt wedging. I spend a lot of time in the desert areas or arid areas. I hate poison oak. And so, where better to go to stay away from poison oak and have lots of good rock exposure is out in the desert regions. Now, every time it rains, it mobilizes, or, heavy dew or something, it mobilizes the salts. And then they end up with the water inside cracks. The water actually evaporates away, but the salt forms its regular repeating internal structure, which is also expansive. And so it will act like a pry bar and, crack the rocks. Now, sometimes you can pick up pieces of these shattered rocks and see actually the white, flaky salt material. So if you were, dying from lack of salt out in the desert from sweating too much, you could actually lick this stuff in some cases and, it'd be good for you if you had enough water also. Because you need salt too. So Death Valley, we take field trips out to Death Valley and we show students this. So salt wedging. All right, thermal expansion and contraction. The example of this would be if you have an old truck on your property. It probably has a cracked dashboard, okay? And that's because the sun beats down in the day and it expands, and then it gets cold at night and it contracts. And over time, the same stuff happens to rocks and they can crack. This is especially bad in areas with huge fluctuations in temperature. It's hot, hot, hot during the day and very cold at night. A lot of desert regions are like this. But it can happen a lot more quickly when you have a fire. And that fire can heat a rock up maybe to 2,000 degrees Celsius and just shatter it. All right, I like this, biologic activity, root wedging, okay? All you need is a crack. Remember, this is granite. Granite has a lot of cracks in it, a little bit of leaf litter, and a seed. And before you know it, you've got a tree growing. And yeah, those tree roots will grow and will force apart huge blocks of granite. So root wedging would be a great example of physical weathering due to a biological agent. All right, so be able to name and briefly describe two of those. Not too bad. All right, chemical weathering. Chemical weathering is the chemical breakdown of a rock, and you end up with very different material. Now, once again, I'm going to tell you about different types. I'm going to tell you about 4 different types of chemical weathering, and what you need to know is 2 of these. So be able to name and briefly describe 2 types of chemical weathering. Now, we've talked about 3 of these 4 types before. Oxidation is just rusting. Dissolution is when I talked about dropping acid on things and they fizzed. Solution is when I talked about dropping things in water. Water is the universal solvent. And then the last type is how we make clays, and I'll tell you about it. All right, oxidation. Oxygen is a chemically reactive element, and it's pretty common in our atmosphere now, and it really kicks the behind of anything that contains iron. So mafic minerals, we're going to find out they are going to get their butts kicked by all of the 4 forms of chemical weathering. Now, so oxygen combines with iron to make oxides, or iron oxide in this case. And so rusting actually is a chemical breakdown. You guys, if you jump on a rusted bike, it may just fall apart. It's not the same thing as a non-rusted bike. All right, the Southwest is famous for its red rocks, and the red is from the iron that has been rusted. In some cases it's a stain, in some cases it's an inclusion in there. All right, dissolution. Dissolution is what acid does. Acid is any molecule that can break a hydrogen ion off. Okay, so we use hydrochloric acid, or HCl, in lab. We drop it on things to see if they fizz or how they react. And so the hydrogen would get in there and break apart weak bonds. Okay, so things like if I dropped a calcite mineral into a vat of acid, it would completely break apart. Okay, stronger acids break off more hydrogen ions. All right, the solution. Water is the universal solvent. Anything that's ionically bonded can be broken apart by water. Great example of this is my beautiful halite crystals. If I have beautiful cubes of halite and I toss them in a bucket of water, I will end up with no cubes of halite and, salty water. So water is the universal solvent and breaks apart simple ionic bonds because they are weak. All right, hydrolysis. Hydrolysis is kind of cool. Water does two things. Water acts as an acid. Remember, H2O or HOH is water. And water breaks into H plus and an OH minus, and then water acts as the universal solvent. And so it really gets in there and breaks apart ionic bonds. If you remember those 8 igneous minerals that we talked about before, quartz, which is completely covalently bonded, is the only of my igneous minerals that is not at all affected by any of these 4 types of chemical weathering. That's why we end up with quartz sand beaches in Northern California, because the granite gets broken down into quartz, clay, and ions in solution. The quartz can't be broken down any farther than just SiO2. So by water acting as both a solvent and as an acid, it just kicks the butt of anything with ionic bonds. So if you kind of think about all 4 of these types, the mafic minerals have lots of ionic bonds and lots of iron in them, and they really just get their butts kicked at the Earth's surface. All right, there are 3 different factors that control the rate of chemical weathering. Now, guys, I forgot to mention before, physical and chemical weathering happen together, okay? And in fact, chemical weathering loves physical weathering. Sometimes we're going to talk about, sometimes it's more physical, sometimes you have more chemical weathering, but they can occur together. Now, chemical weathering loves physical weathering because physical weathering breaks rocks into smaller parts, and smaller pieces means more surface area. That's exactly what chemical weathering works on. It works on surface area or exposed surface of a rock, and the smaller pieces you break it into, the more surface area it has to volume. All right, climate. When it's hot and wet, chemical weathering happens really, really fast. If you're a rock climber, you typically don't climb in hot and wet climates, like, Vietnam, for instance, because the rocks are just, weak and broken up and you can't climb. Chemical reactions happen faster in higher temperatures, and with the with more water around, chemical reactions happen more rapidly also. All right, and the last factor that I've been hinting at is the parent material. The more iron and magnesium minerals, rich minerals that are in those rocks, the more they're going to be chemically weathered, okay, which means the more broken down it's going to become, because they're full of iron and magnesium, they're got more ionic bonds, and they're also formed at higher temperatures, and so they're just not happy at the Earth's surface, so they're not real stable. All right, so this slide just shows you that if I have, maybe a granite, let's say, what am I going to end up with if I chemically and physically weather it? I'm going to end up with smaller pieces of granite. I'm going to end up, if I chemically weather it, with quartz grains, clay, and compounds or ions in solution. If you look at the bottom, the original material, feldspar. Feldspar has ionic bonds, so it's going to become clay and ions in solution. Iron-rich minerals, mafic minerals, are going to become clay and ions in solution. Okay, white mica is going to become clay and ions in solution. Okay, quartz you just break down to smaller pieces of quartz, completely covalently bonded. It gets physically weathered but not chemically weathered. Now, calcite you don't find in granite, but calcite is that mineral that if you drop acid on it, it fizzes, and it's just going to break down into its 2 ions, the calcium and the carbonate. All right, now erosion, you guys. Erosion is really, really important. We'll talk about erosion later a little bit. People get PhDs in erosion, but erosion is just the act of picking up and starting to move those weathered pieces. And obviously, the smaller the pieces of pre-existing rock, the easier it is to erode them. So what's much, much more important is the next slide, which is transportation. Now, there are 4 main agents of transportation, and I do have another video for you that kind of talks about the 4 main modes of transportation and some specific characteristics of each of these. Now, wind, you guys all know that particles get carried by wind, but only small particles. Water, everybody's seen a river in flood and seen it moving boulders, or you see a typical river just carrying silt and clay or maybe ions in solution. Ice, okay, our last ice age was not that long ago. Glaciers move materials, move sediments and rocks. All right, and then gravity. Gravity, things like rock falls. All right, be sure to watch that video that I made. So wind carries small grains of silt and clay, and it's also an excellent sorter of these small grains. Remember that if you have a sand dune and it's in a windy area, typically it's just sand. The silt and clay has been picked up and moved elsewhere. Water can potentially transport any size class of sediment depending on its velocity. Okay, so obviously like a stream and flood has a higher velocity and therefore would carry a larger size class than, a calm, gentle stream that has a lower velocity and would only carry smaller size classes. Water is an excellent sorter. Okay, meaning that it separates out these sediments according to size, but also according to density, which is kind of important considering we're in Placer County, a site of mining of water-laid sediments. Okay, the other thing about water is it rounds the sediment. So if you find a really beautiful rounded large rock, it was probably rounded in a pretty powerful stream. All right, ice. Now, right now on Earth, there are glaciers, and in the past, there are a lot more glaciers on Earth, and ice will pick up any size class and transport it. It does no sorting, no rounding at all. So when the ice melts, it just dumps behind everything from clay, silt, sand, cobble, gravel, boulder, etc., and it doesn't separate them out at all. All right, and then gravity. Gravity typically is step one. There's a large rockfall. All size classes come down. But later on, if it's windy, it'll remove some of the fine stuff. And then it rains, it'll remove the sand-sized stuff. But you typically don't get a deposit just from a gravity fall. Okay, so that is another mode of transportation, but typically another agent picks up farther. All right, and while we're continuing to transport, we are continuing to weather these rocks, to kind of break them down either through abrasion or maybe dissolution or something like that. Now, when you find a sediment that's been deposited, you can typically tell quite a bit about what agent moved it and how far it was moved and what was the energy of that agent. You see this a lot in river deposits. And so I'll try to show you guys a picture. A rock called a conglomerate is a river deposit, and typically the pieces are pretty large. So you would know, because the pieces are rounded, that it was transported by a river. It was by a pretty powerful energy river if the pieces are large, and that the rounder they are, the farther it was transported. So it's kind of neat to be able to read the rocks this way. All right, when does deposition occur? Deposition occurs when energy drops. So let's say we have a river and flood and it's carrying all size classes, okay? Everything from clay, silt to boulders, okay? And then eventually the flood will ebb and the energy will drop, and the first thing that'll fall out would be the boulders, okay? Then the cobbles, then the gravel, then the sand, until it was so low energy that all it was carrying was silt and clay. And when that energy dropped too, then it would drop the silt and clay. So as energy drops, you drop out the largest size class. So this is why, when you go to Lincoln, okay, Lincoln is famous for its clay. And the clay was formed, the clay deposits were formed 50 million years ago, because Lincoln was actually the mouth of a river. The ocean used to be right there. Okay. Now, if you guys go up Highway 80, the Gold Run rest stop, we can find part of that 50-million-year-old river up there. That huge road cut right by the Gold Run rest stop is the higher energy part, the gravel plus part of that same river. Okay, so pretty neat when you know what you're looking at. All right, obviously, if you're going to deposit sediment, typically more sediment gets deposited on top and more, and so you end up burying it. And when you bury something, think about it. If you guys have ever played, tackle football and you end up at the bottom of the pile, sometimes you get the wind knocked out of you. Your lungs are big, open, empty spaces in your body, and so they get compacted. And that's what happens with sediments. The more on top, it gets the air and the water driven out, and the sediments become much more close together. You lose any pore or open space. All right, now sometimes sediments are just compacted enough to make them cohesive and turn into a rock or lithify. But other times, in a lot of cases, you do need a cement. Okay, and that cement can vary quite a bit, and it's kind of a thing you'll talk about in lab, or if you come into my office hours or something, we can talk about it. But you can be cemented. But what matters here is lithification is the act of taking those sediments and turning them into sedimentary rock. So it is important. Okay, you can get a PhD in lithification. Obviously, we're not going to cover it that much here. All right, so we are ready to start talking about the different types of sedimentary rocks: clastic or detrital, chemical, and biochemical. Now, if you remember back to the rock cycle, we said that sedimentary rocks are made up of pieces of pre-existing rock, and that's true, but that definition really only fits number 1, because in the case of 2 and 3, those pieces are really little. They're those ions in solution. So, pieces that you would think of like, sand making sandstone or clay making shale, that really falls under the clastic or detrital. So if you remember clastic means piece. All right, chemical sedimentary rocks form from precipitation. Now, you guys have all gotten a mouthful of seawater. Blech, tastes awful because it's so salty. Okay, if you take that and you put a bucket of seawater and you let all the water evaporate out, you're going to end up with some white crusty stuff. Those are chemical sedimentary rocks. They have formed solids from ions in solution in what was once that seawater. All right, and then the last case, biochemical. The bio is what makes it different from the chemical. Bio means life. These also precipitate from solution because of organisms or life, and we're going to talk about that. Chalk is a great example. When you guys write with chalk, you are smearing the carcasses of hundreds of thousands of little organisms all over the chalkboard. Now, don't worry, you're not hurting them. They've been dead for millions of years, but if you looked at a piece of chalk under magnification, you guys would see little skeletal pieces. It's pretty cool. All right, so clastic or detrital sedimentary rock, they're made up of pieces of pre-existing rocks and minerals. Okay, so we kind of... All right, we also classify classic sedimentary rocks. We look at a couple of their characteristics, and we've talked about these. Grain size, fine is silt and clay, medium is sand, and coarse is gravel plus in size. Sorting, okay, sorted we mean uniformity of grain size. If all of the grains look exactly alike, we call that very well sorted. If you've got every size class known to man, we'd call it unsorted or very poorly sorted. All right, and then rounding. You all know what a beautiful rounded river rock looks like, and then you probably know what an angular shard looks like, and we'll talk about what those tell us. All right, so grain size, it tells us about the energy of the transporting medium. You have to have a strong energy to carry a big piece of sediment, and you can have a weak transporting medium to carry a small piece. Okay, so rivers are kind of easy because they do carry all size classes. The stronger the velocity of the river, okay, the bigger the size grain. And the weaker the velocity of the river, the smaller the size grain. So you look at your deposit, it's a sand, you would know it's a medium velocity. You look at your deposit and it's gravel plus size, then you'd know we're looking at a very strong velocity or high velocity, a fast moving river. All right, so coarse, medium, fine. Again, we have the scale that we use as sedimentologists called the Wentworth scale. And it really does. It's a little bit more complex than this, but it really honestly breaks it down to this. You guys, we're simplifying but not lying. So if you look at this is still pretty simplified from what I would use as a sedimentologist. Okay, but instead of teaching you all these, like, if it's between a 64th of a millimeter and 2 millimeters, it's sand, we just tell you fine is silt and clay, medium is sand, and coarse is anything gravel and above. Okay, now clay is finer than silt, okay, so it's even smaller. And I don't use the word mud, but sand, and then kind of gravel, pebble, cobble, boulder, and kind of generically they put all that together as gravel. Okay. All right, now we're going to learn some specific rocks. This is a river deposit right here. It's called a conglomerate. Now the entire piece there, and I'm sorry there's not a scale, I'll tell you what this looks like. The entire piece there is pretty large. It's as big as your head at least. And the individual round dark colored pebbles that you can see in there are bigger than a quarter. Okay, so what a conglomerate is when you have rounded, large gravel plus pieces in it. Now, see all that kind of yellow matrix? That is the cement that holds it together. So when you look at a rock like this, you don't look at this one piece and say, oh my God, it's huge. You look at the individual pieces in there, the individual sediment pieces. And so they're large, they're rounded. So we know that they were deposited by a river. Okay, because they're rounded and large. They were carried far from their source because they are very rounded. And that it was in a fairly high energy stream because this is a pretty big size class to be carrying. So this is a conglomerate. All right, what happens if they were angular? Now, I did include a scale on here. These are big pieces. What the sediment is the white fragments, and you can see they're angular, so it's not a conglomerate. And then the cement is the purple stuff. Now, first of all, you noticed before that the conglomerate was also well sorted. I forgot to mention that. This is not well sorted. I have every size class in here practically. It's angular, so this definitely wasn't carried by a stream. It wasn't carried far. The other thing to notice is that the white fragments are all the same stuff. In that previous picture, the pebbles that were in that conglomerate were very different because it had drawn from a much larger drainage area. Where maybe this was actually could have been a gravity fall. It just fell into a low-lying place, got very compacted and lithified. So again, large pieces that are angular are called breccia or breccia. All right, here's a sandstone. Now, this sandstone happens to have layered appearance because of different oxygen levels. It can get oxidized or rusted when there's high oxygen levels. You see the red layers. If you touch this, you would know it's sandstone. It feels like sandpaper. So the clast is not the big piece that's in here. Again, this would be about half the size of your head. It's pretty big. It's the individual grains. And if you rubbed your hand over this, you would actually, pop off different pieces of sand grained. Okay, so they feel like sandpaper, and you can usually, in some cases, pop off individual sand grains. And if you look kind of on the tabletop in the foreground, you can actually see some sand grains that have fallen off of this. All right, so remember sand is medium. All right, so fine grain or lower energy is shale, and shale is also known as claystone. It's made up of clay. So the individual pieces in here, you'd actually have to go microscopic. Now, shale, being made up of clay, has a certain property that it breaks in these flat sheets, and it's called fissile. Clay is a mineral that looks a lot like the white mica. Okay, and chemically, it's very similar to the white mica. It's just microscopic. And so those little flat sheets lie down on top of each other, and then they break flat. Shale is an excellent sedimentary rock for finding fossils. Some of the best fossils preserved ever have been found in shale. Okay, and that's because it's so fine-grained. It would cut off oxygen and water, and this, the biological material wouldn't rot, and it's just a great rock for finding fossils. All right, sorting is the uniformity of grain size. And we also got to throw in a density because, when you deal with gold country like we are, gold is, I don't know, not quite 10 times, 8 times as dense as quartz. And so it's going to get dropped out at a different rate than size. Okay, so at first we'll talk about sorting according to size. If you look at a sandstone and you look at the pieces underneath a microscope, let's say, and they're all exactly the same size, that would be a very well sorted sandstone. Okay, and again, why would we sort? Because energy drops. If I wanted, rounded river rocks that were 7 inches across, okay, not 3 inches across or 5 inches across, these oblong pieces, I'd have to go to a certain place in the river where the energy level dropped and dropped out those size classes. And if you guys walk along the river, you can actually probably find areas like this where you have different size classes. All right, so here, I'm not crazy about this. Being a sedimentologist, I would definitely not call that very well sorted, very well sorted. I've seen samples where they're exactly the same, but I definitely agree with that, very poorly sorted. That might be something you would see if you had a glacial deposit. Just dump it there, okay? But as you go from the bottom right to the top left, kind of reading backwards, you can definitely see that you get less and less size classes, and you get a little bit more uniform as we change. So the scale's not quite right, but it works. All right, then rounding. And again, I'm a sedimentologist. I don't quite like this, but I think the tables that I used to use would scare you. They're pretty complex. So you guys all know that if you take a hammer and you break, let's say you break a quartz crystal, you got sharp angular shards. But if that quartz crystal, that broken up quartz crystal was now to be tumbled in a river, eventually you'd get this beautiful rounded, maybe either an oval or a sphere around rock. And so remember, rocks get rounded in rivers because it tumble and they get abraded, and it's just like a rock tumbler. Okay, it basically smooths out all the rough parts. And so the farther a rock is transported, like in a river, the rounder it is. All right, our second type of sedimentary rock are chemical sedimentary rocks. And chemical sedimentary rocks are rocks that precipitate from solution. Okay, it sounds scary, but it's really not. Now, precipitate is a word that has been hijacked by weather people. If they say expect precipitation, you're like, oh, it's going to rain. Okay, and all that means is that water vapor turns to liquid water. Okay, so it goes from gas to liquid. That's a phase change. And in this case, ions in solution, kind of in a liquid form, go to solid. Okay, and that's a phase change. And there's lots of different ways. I gave you guys the evaporation. If you remove the H2O out of there, you're left behind with the salts that form. But temperature changes, chemical changes can also do this. Now, when you're out in the field and you come across, salt deposits or gypsum deposits or something, you are finding them where they were deposited. Okay, so it's not like they could be transported. If they're transported, it's because they're put back into solution, moved, and then reform, and then that's their new place of being formed. So water that has a lot of dissolved substances in it, like the ocean water or an inland sea or something like that, would be a great source. All right, common sedimentary, chemical sedimentary rocks would include limestone, although we have to be careful. Limestone sometimes is biological. But if you remember, early on, we got rid of a lot of the carbon dioxide in the Earth's atmosphere before life came about by forming limestone or calcium carbonate. Okay, chert. We have a lot of chert in California. It's microcrystalline quartz that precipitates from solution. Now, again, it's SiO2. Sometimes it can be biological too. All right. Now, rock salt and gypsum are never biological, so they are always chemical. Now, I am going to show you guys a movie that I took when I went to what was Lake Mead that had almost dried up completely. And this is how we get a lot of our samples. I'm collecting rock gypsum. Okay. So here I am trying to pry some of this out, and as that lake level drops and the solution or the concentration of the dissolved substances becomes so great, they'll actually fall out and form a solid. And so look, it looks kind of like ice. That's actually gypsum. Okay. All right, and then here's rock salt. So halite is the mineral that goes into forming the chemical sedimentary rock salt. All right, biochemical, you like chalk, okay? They precipitate from solution by life or by organisms. Okay, what happens? If you're a little organism that makes chalk, you are a coccolithophore, okay? Your shell is made up of calcium carbonate or calcite. And you're in the ocean, and there's calcium and carbonate in the ocean, but they're separated. And so you expend energy. You pull calcium, you pull carbonate, you stick them together, and you stick them on your body to make your shell. Okay, so when you die, your little carcass falls to the seafloor. The biological part probably rots, but the hard part, this little shell, can get buried, compacted, and lithified. And that's actually how we get our chalk deposits. All right, so limestone, again, it can be chemical or biochemical, but if it's chalk or if you can see fossils in it, then you know that this is biochemical. It's made up of the shells of organisms. Most organisms in the ocean actually do make their shells out of calcium carbonate because it's pretty common. Now, in California, we have something different. Our water off our coast is very, very cold. And the organisms off our coast, actually, some of the ones that are really important make their shells out of little teeny bits of silica, okay, or microcrystalline quartz. And so again, they expend a lot of energy to pull that silica out of the water and glue it onto their shells. Now, diatoms, you guys, I have a lot to be thankful for diatoms. I like to breathe oxygen. Hey, thanks, diatoms. Diatoms in the Pacific Ocean make more of the oxygen than, the plants around us. Okay, you put gas in your car today. Hey, thanks, diatoms. Diatoms are photosynthetic organisms that live in the ocean. Okay, they have to live in the zone that's lit, so they have a little bit of oil in their body. Okay, that keeps them floating because it's less dense. When they die, they fall to the sea floor. Okay, their little shells are made of silica. They get buried, compacted, and lithified. But during that whole process, the oil gets changed into petroleum. So we have these guys to thank for the oil and gas that we find off our coast. Now, the other thing is if you have a swimming pool, it probably has a filter made out of diatomite or diatomaceous earth. So lots and lots of uses for that. And it's a major resource in California and Nevada. It can be organisms that, diatoms can be freshwater or saltwater, and they make their shells out of silica. So very important organisms. All right, now bioclastic, whoops, there's a misspelling, sorry about that. Coal is bioclastic, not biochemical. Okay, so coal, we can ignore the oil shale for now. Coal is just a bunch of dead plants from the past that are buried, compacted and lithified. They're buried in a environment where there's no oxygen to cause them to rot out, like a coal swamp or a muddy swamp. And so if you wanted to study, really older than dinosaur plants, okay, plants that pre-existed dinosaurs, you might actually go to a coal mine in Virginia or in Pennsylvania and start pulling apart coal seams, and you'll find fossilized plants because that's exactly what coal is. Okay, so that's more bioclastic, not precipitated from solution, so not chemical. All right, now here's a limestone. If you drop acid on it, it will fizz, but obviously you guys can tell that this is biochemical versus chemical because, boy, look at those organisms. All right. All right, we are ready to start talking about metamorphic rocks. So let me go ahead and bring in the bullets. All right, metamorphic rocks are rocks that change. You can have a sedimentary rock get metamorphosed, an igneous rock, and you can even get a metamorphic rock further metamorphosed. Typically, it's pressure and temperature. You subject them to higher temperatures and pressures like you would find deeper and deeper inside the earth. And this would cause the minerals to become uncomfortable and to kind of reorganize in a solid state, not melting. Okay, but hot water, okay, chemically active fluid, hot water, basically can do this also, and it can do it at depth and it can do that at the surface. That's a little bit more specialized, and again, if you go on in geology, you talk a lot more about chemically active fluids, but the main agents are pressure and temperature. All right, so remember that we are changing, but we are not melting. It's a changes in the solid state. So nearly all metamorphic processes occur deep in the earth because as you go deeper, it gets hotter, and as you go deeper, you've got the weight of the overlying rocks are getting more and more, and it's under more pressure. All right, now you guys, you have a handout that I scanned about metamorphic rocks, and if you notice, the very first column is parent rock. And in fact, when I look at a metamorphic rock, it's not the name of the metamorphic rock that first comes to mind, but it's actually the name of the parent rock. Okay, so I'll kind of explain. It's pretty easy to identify a metamorphic rock because it varies only slightly from its parent rock. Now, most of our changes are going to be textural changes, okay? But once in a while, especially with that chemically active fluid or water, they can be mineralogical. Now, 99% of what we're going to talk about today are strictly textural changes, okay? An example, you've got the makings for chocolate chip cookies, but you could actually make chocolate chip cookie bars, okay? Same ingredients, just something a little different. Okay, but if you have the makings for chocolate chip cookie and I say, make me steak and fries, okay, you can't make them. You don't have the right ingredients. And so when I look at a metamorphic rock, I know what the parent rock is because you can't change the chemistry. You're not changing the minerals. You're just changing the texture. Okay, so if you gave me the chocolate chip cookie bars, I'd say, oh, you had the makings for chocolate chip cookies. Okay, so the chemical formula won't change. It will just be the texture that will change. All right, now this is called the geothermal gradient, and what's kind of cool is, and we're going to talk more about this in some further sections, let's pretend that this was the United States or North America. Okay, the North American continent. Now think about the North American continent and now picture kind of near the Great Lakes. Okay, the Great Lakes are in the center of the North American continent. And, you know, tectonically, it's pretty boring. They don't get volcanoes, they don't get a lot of earthquakes, or probably not very many earthquakes at all. That's the oldest part of the North American continent, and it's not active. We're going to find out the edges of the North American continent are much more active. But you know what? The deeper you go, the hotter it gets. So if you look, the deeper you go, the hotter it gets. Then if you look at the far left, the amount of overlying pressure, or the weight of the overlying rocks, it also increases, and that's going to increase constantly. All right, let's go to the Rocky Mountains or the Cordilleran. Okay, the deeper you go, the hotter it gets. But check it out. If we went all the way to the bottom of this graph, it's 1200 degrees. But look to the right. The same depth is only 600 degrees in the stable interior, or the craton, the center of the North American continent. Okay, why? Because there's some tectonic activity going on, and that's pushing up those mountains. Well, let's go out to the Cascades, okay, and that would be the basaltic volcanic region, and we're going kind of towards the west. Look at the same depth. It's 3 times as hot as that stable interior of the continent, and that's because there's a lot of tectonic activity. We get earthquakes, we get volcanoes, and these are all signs of action happening. Okay, so you know, different parts, it's going to get hotter, you know, quicker, but no matter what, the basic rule of the deeper you go, the hotter it gets, that holds true. All right, our metamorphic agents, heat, okay, increasing temperature, pressure or stress, and you can have pressure from just the weight of the overlying rock. The deeper you bury it, you could actually eventually metamorphose it. But if you noticed, I showed you the Rocky Mountains and the Cascade Mountains, and these are areas where things stick up, and they stick up in, you know, height, elevation, because you've got some squeezing or what we call differential stress, and I'll show you guys hopefully a slide of this, and that's extra stress, okay, or so differential stress. And so that will even more so increase, and we're going to get a lot of metamorphic rocks where you have mountains sticking up. All right, and then chemically active fluids, hot waters. Hot water really dissolves a lot of materials in it, and so that it can, you know, go through a rock and strip stuff out, or it can go through a rock and deposit things. So it can change the chemistry. Okay, if we had, it'd be kind of like taking a trip to the store. You got chocolate chip cookie makings. I want steak and fries, but I let you go to the store. You could make me steak and fries. Okay, so this changes your ingredients. This changes the chemistry. It can be like a, you know, somebody goes in your pantry and steals stuff, or it could be like, hey, a supermarket trip and you get to, you know, refill your pantry. So it just kind of depends on what's going on. All right, so there are 2 major metamorphic settings that we're going to learn about, and the first one is regional metamorphism. Now, regional metamorphism is large-scale metamorphism. Okay, I'm going to picture the North American continent. We have the Cascades, we have the Sierra Nevada, we have you know, the Rocky Mountains, we have the Appalachian Mountains. Okay, these are all areas, very large areas that would have a lot of metamorphism involved with them. So regional metamorphism is areas around mountain buildings, the Himalayan mountains, the Andes mountains, where you're going to have temperature and pressure both playing a role. So these are going to produce huge amounts of metamorphic rock. Okay, so both temperature and pressure playing a role. We're going to learn, there is a smaller example where just heat plays a role. Okay. All right, there are two types of pressure that you can have. You can have just the pressure from increased weight of overlying rock, and we can cause metamorphic rocks that way. But in a regional metamorphic setting, you've got the bottom type of pressure also, something called differential stress. Now, when mountains stick up in all those areas that I was naming, it's basically because of plates pushing together. And you guys can see that shown by some larger arrows in the bottom picture there. And so when these things compress or push together, they shorten and thicken the rock, and you can see that now it's sticking up kind of like a mountain. And so that's called differential stress, and differential stress makes mountain chains, and differential stress makes huge amounts of metamorphic rock. Now, differential stress, it can create a very specific type of metamorphic rock that you can identify due to its texture, and we're going to talk more about it. But remember when I said that you can metamorphose a metamorphic rock? What I was talking about is metamorphic grade. Look on the bottom of your one-page metamorphic rock kind of diagram handout that I scanned for you, and those are the rocks that have this special texture that I'm going to talk about later, but those are exactly the same rocks that have they're the only ones that go through metamorphic grade. Now, metamorphic grade, again, we're going to have a parent rock, and I'm going to give you one parent rock to make your life easier. There could be more parent rocks, especially for the higher grade. And then what we're going to do is we're going to subject it to a little bit of heat and pressure. If I take shale, my one parent rock, okay, that's a sedimentary rock. It's made up of clay. And if I subject that to heat and pressure, I can change it to a metamorphic rock called slate. I think everybody knows what slate is. It's the tabletops, its menus are sometimes written at restaurants on slate boards. Things like that. Old billiards tables or blackboards used to be slate. It's really cool, and it breaks flat. So slate would be the lowest grade. Now let's say that slate got put under more temperature and pressure. It would change over to a metamorphic rock called phyllite. Okay, the texture will change on this. It won't be beautiful and flat anymore like slate is. It gets kind of wavy, and it also starts to get a little shimmery and silvery. All right, if I take the phyllite and I subject it to more heat and pressure, I make a very cool rock called schist. Yes, it's a German word. And schist, some schist, my favorite schist, looks like silver and black sequins glued together. Okay, it's really shiny. It's got this property called schistosity, which makes it really like winking and winkly at you, or shiny. Now, if you take that schist and you further metamorphose it, okay, more heat and pressure, you make a German word called, or a rock called gneiss. Okay, yeah, that's nice. Now, if you take that gneiss and you heat it up more, you're going to end up melting it. Gneiss is my highest grade metamorphic rock in this series that I can get. And so, yes, shale, if you metamorphose it enough, can, form slate, phyllite, schist, or gneiss. Okay, so this is metamorphic grade. It doesn't have to, you can take shale and take it right to gneiss. You can, it doesn't have to go A to B to C to D, but this is the scale that, a little more heat and pressure, a little more heat and pressure, you can go basically from a slate all the way up to a gneiss. And this can happen in one of those mountain building areas. The deeper we go, the deeper into the earth we go, more overlying pressure, more heat, etc. So we may end up with, folded sedimentary rocks at the surface, but just underneath the surface we'd end up with slate, and then farther down phyllite, farther down schist, and farther down gneiss, before we were so far down that it would melt basically. All right, my second metamorphic setting is contact metamorphism. This is a smaller scale, and this occurs when you just have a hot body of magma, some hot source, and it's a small scale. So if you have just a blob of magma that's come up, it's in contact with older rock that's colder, it can actually melt some of that maybe even, but what it doesn't melt, and it just changes would be the contact metamorphosed rock. Okay, so temperature is the only thing playing a role. It's not pressure. Pressure is not playing a role. This usually happens. It's not real common, but it does. You get random blobs coming up of magma. It's typically, being placed pretty close to the Earth's surface and just really small scale. Okay, so here's just an example. You notice there's no major mountain building event going on. We don't have mountains sticking up. You have this hot magma intrusion. And see that contact metamorphosis zone? That's kind of like a halo surrounding this rock. Rock's a pretty good insulator, and you get far enough away from that magma body, and the rock's not changed at all. But obviously right next to the magma body, you will have some changes occur due to the contact with that heat. Okay, so pressure's not really playing a role because it's all pretty close to the Earth's surface here. And you definitely don't have any big arrows squishing, compressing, coming in and forcing mountains up. Okay, so much smaller scale. Doesn't make as much metamorphic rock. Okay, kind of gives it this halo-like shape. All right, remember with the regional metamorphism, the same exact rocks that make my metamorphic grade are my only foliated metamorphic textures. Now, fall foliage, everybody knows about that. Foliage means leaves. And if you kind of took a bunch of leaves and you just kind of stacked them up on top of each other and you looked at them sideways, you say, hey, I've got a stack of leaves. Well, that's sort of what this texture looks like. You've got flat minerals, and you basically, because of those directed pressures, those big arrows, you align them perpendicular to those big arrows, and you just have this pile of flat minerals. And you can look at the sides and say, hey, I see those flat minerals lined up, and I can see which way the big arrows would have come in. It had to be perpendicular. So check out this slide. I've got a parent rock of granite. I subjected to those big arrows. We're making it in a mountain building zone. This is all happening in the solid state. The minerals migrate, and the minerals move and realign, and they're growing in the direction of least pressure. Minerals don't fight the system, they go with it. And so look at how you can tell which way the minerals align, perpendicular to the big arrows or perpendicular to the directed pressure, stress. And so if you find an in-place foliated metamorphic rock, you can walk right up and figure out which way the big arrows were, which way the directed pressures, perpendicular to the alignment of those flat, long, lean minerals. Alrighty, I don't think this is going to work. So I will try to make sure on your Blackboard that this works, or on your PowerPoint. All right, now non-foliated textures. When do I get non-foliated textures? Two reasons. I could get non-foliated textures if I do not have directed pressures, but there's another way. Some minerals are short and fat. We call them squatty, equidimensional. And no matter what you do to them, they will just be short and fat. Yeah, they can grow in size, but they'll just, as they add height, they'll add width. Okay, and so to get a non-foliated texture, a contact metamorphic setting would give you a non-foliated texture. Okay, because it doesn't have any directed pressures to make any long, lean minerals line up. But either of those metamorphic settings can give you a non-foliated texture if all you're dealing with are short, fat minerals. Okay, and those would include quartz and calcite. Okay, they are short, fat minerals, and so they will never look like a bunch of leaves on the side. Now, here's a photomicrograph. You take a very thin slice of a rock and you attach it to a glass plate, and then you kind of sand it down, polish it, and let light go through it. On the left-hand side, you have a foliated texture. Okay, and if you take your fingers and point your finger in kind of the top right-hand corner and then the bottom left-hand corner and squeeze them together, that's kind of the directed pressure direction because it's perpendicular to the alignment. Now on the right-hand side, I have short fat minerals, and so that's a non-foliated. There's no lining up. That's a true mosaic. All right, so here's some slides. Let's look at them. On the top, we have my metamorphic grade and foliated. They overlap. They're the same thing. And look at the pictures, you guys. Where it says texture, you can really see the alignment, and you could figure out exactly which way the directed pressures. They'd be coming from the top and the bottom. Now look down at the non-foliated pictures, okay? And what you see are short, squatty guys, minerals that just grow together, you know, in a mosaic, okay? And again, who are my non-foliated? Marble is calcite. Quartzite is metamorphic quartz. Anthracite is metamorphic coal. Okay, and that's something you hopefully will see in lab. So check this one out, because this in your handout that's in the folder are pretty important. All right, so again, we were talking about slate, phyllite, schist, and gneiss. I think I'd like to show you guys some pictures. Well, here's the gneiss, okay? And the gneiss, you see the black and white banding? This is the highest grade metamorphism. If I take this too much higher in temperature and pressure, of course, those white minerals are going to melt because they're lower temperature, and so then it's not going to be a metamorphic rock anymore. But in this case, in the solid state, the light and dark minerals have migrated to be with their own kind. And so again, you get this what's called gneissic banding, or the black and white striping, kind of a zebra rock. All right, and then here are, let's see, this is a not a very good marble, but this is a marble, pretty good sized pieces of, it would fizz with acid, and it's got a kind of a coarse grain